AP Calculus AB, let's look at some examples of optimization. Construct a box whose base is a square and has a volume of 36 cubic feet. The box having a volume of 36 cubic feet, that's the constraint for this. The material used to build the top and the bottom cost $8 a square foot, and the material used for the sides is $6 a square foot. Determine the dimensions, so that's important. Determine the dimensions that will minimize the cost to build the box. So let's draw a box first. It says that its base is square, so they have the same dimensions. I'm calling those x, and I'm going to call the height h. We need an equation that represents the cost. So c of x, or c, is going to equal this first part here, $8 times 2x squared. So let me explain. It says it's $8 a square foot for the top and the bottom. The bottom is the square, its dimensions are x by x. So the area of this bottom is x squared. There's also the area of the top, which is also x squared. There's two of those, so that's why this is 2x squared. So this is the area of the top and the bottom combined. And then for every square foot, it's $8, so we're multiplying it by 8. If we add to that $6 a square foot times 4xh, the xh comes from the area of one of these sides, the lateral side. Base times height is x times h, and there are 4 of those: front, back, right, and back. Front, right, left, no. Front, back, left, and right. So there are 4 of those times the xh, and there's $6 a square foot. If you simplify it, then here's your cost function. Then we want to figure out a relationship between x and y with the constraints. Well, to find the volume of a rectangular prism, take the area of the base times the height. Base is a rectangle, x times x is x squared, times the height is h. It says this volume is supposed to be 36, that's why we put 36 in for v. We get one of the letters by itself, h is the simplest, so we get h is equal to 36x squared. We're then going to plug this into the h value here, which gets us to step 3. So the cost function is going to be 16x squared plus 24x. We replaced h with 36 over x squared. We can simplify this a little bit. 24 times 36 is 864, and we can cancel an x from the top and the bottom. We get 864 over x. And so I can use the power rule. I'm going to rewrite this as 864 times x to the negative 1. Step 4 was to find critical values and figure out if those critical values are mins or maxes. So we take the derivative, it's the power rule. I want to make this into one fraction, again in common denominators, and that gets me to here. So to get common denominators here, once again, I move this x squared to the bottom, and then I multiply the top and bottom of this fraction by x squared, so I have common denominators. Once they're common, the bottom stays the same, and I subtract the top numbers. And then to make this easier, I factored a 32 out of this numerator and got 32 times x cubed minus 27. We then want to figure out what the critical values are. So we got c prime equal to 0 and c prime undefined. Undefined, set the denominator equal to 0, and for it to be equal to 0, set the top equal to 0. And end up with the critical value here of 3. Now to use the candidates test, I would need to have a good idea of what my boundaries are for the values of x. And I could certainly say that the smallest value of x is 0. The largest value of x gets a little complicated. So I could say that it's 6, and that would make sense, but I don't want to think about it too much, so I'm going to use a different method here. I'm going to use a first derivative sine diagram. So I got my beginning boundary 0, I got my critical value of 3, and let's just say that I don't know what my top boundary is, so it's going to go to forever to the right. If I put a test point in of 1 into this here, the bottom's going to be positive no matter what. If I put a 1 up here, it's going to end up being a positive times a negative, which is negative. If I put a 4 in, 4 cubed is bigger than 81, is bigger than 27. So it's going to be a positive times a positive divided by positive. So it's going to be positive here. Here's what we know. If it's negative on the left of a critical value, let me rephrase that. If the derivative is negative on the left of a critical value and positive on the right, that means that there is going to be a minimum. So this is only one critical value. Could have been a max, could have been a min. Apparently it's a minimum. So if we try to answer the question, which is what are the dimensions? We're saying one of the dimensions is 3. The base is 3 by 3. To find the other dimension, I take my constraint and I replace the x value with 3, and that's going to end up giving me a height of 4. The cost is minimized if the dimensions of the box are 3 foot by 3 foot by 4 foot. Let's do another. This is a calculated problem. Distance on the coordinate grid. The equation y equals x squared plus 3x minus 5 contains a parabola. That is our constraint for this. Name a point on the parabola that is the closest to the origin. Closest is referring to a distance. So our main equation here is going to be the distance formula. The Pythagorean theorem, if you will, solve for d. Our constraint, we were given explicitly without doing any work. Step 3 is to try to make this into one variable. So I'm going to replace y here with this mess, and that gives me this. I don't want to multiply this out. And I don't have to because I'm going to use a calculator for this. So I'm going to put into y1, this original function, and into y2, I'm going to ask the calculator to find the derivative. And I haven't checked this recently. I don't use my calculator much, but I'm pretty sure it's n deriv followed by the function you're taking the derivative of with respect to what variable, at what value. We're saying all values of x. Now, in order to find the minimum for this, we are going to graph the derivative. So I'm going to make sure this is highlighted. And when I graph it, it looks something like this. Crosses the x-axis at about -4, about -1.6, and about +1.1. So what are my candidates for this? Well, it looks like my candidates, well, I don't have to worry about candidates. Let me rephrase. This graph goes forever left and right. It's a parabola. So it's not a closed interval. We're not using the extreme value theorem per se. But anytime that the derivative, and this is the derivative, changes from negative to positive, that's a minimum. So that happens in two locations, here, and it also happens here. So the question is, which of those is going to give us the smallest distance? To determine that, we have to take those x values and we got to plug them in to the original function, into y1, if you will. If you do that with the table feature in your calculator, you will find that at 1.152, that's the x value, we're going to have an absolute minimum. The directions for this said to find the point that has the closest value to the origin. So we found the x value here. To find the y value, we're talking about a point on this parabola. So we got to plug this x value into this parabola. And if you do that using your calculator, I believe you get -0.217. So the ordered pair that you see here is the closest point to the origin.